Assalamualaikum warahmatullahi wabarakatuh. My name is Abdul Razak bin Ahmad Syukur, and today I will do the presentation for our task 1, which is the analysis of electric field. So we need to do an simulation using the FEMM simulation, where we need to see two electrodes with a gap distance, and to see how is the density of flux and then the voltage of the electrode. So first here I have already done the blocks. So we have positive electron and negative electron. So the first one I will show is for the gap distance of 1.5 cm. So we can do the mesh analysis, and then we can run to see the simulation. So here we have the simulation of gap with 1 centimeter. So to see the graph, first we will see the graph for the voltage. So we can see here the voltage is declining when the distance increase. So the next one will be the magnitude of field density. So you can see the magnitude of field density is at 3.1, 3.2 e to the power of 6. So I will show for the second one, such as the gap distance of 3.5. So to do that, first we need to move the electrodes until 3.5. So we can select region. Sorry. So take a shift of 3.5. So we need to do the boundary for the positive side. So for the positive side, the voltage will be 3.5 is 97 kilovolt. So 97 kilovolt. Okay. Then we will run the simulation. So and then we will able to see the graph. So we can see it is at the higher voltage at 9 to the e to the power of 4. When the distance increase, so do the voltage. And then the second one is for the magnitude of field density. So magnitude of field density, we can see that the graph start to declining when the distance increase and start to increase back at 3.5 when it reach to other electrons. So that's all from me. Thank you so much.
Assalamualaikum warahmatullahi wabarakatuh. My name is Adib Zaki bin Ziful and my metric number is AE19010. So for today I will explain about simulation for finite element magnitude for task 1. So this shows the simulation with two electrode, this one and this one. This is electrode with radius 25 cm, and this is the air. First we must do the electrode shape using this. Okay, and this is so this is we must set up the material and boundary. This is material is air and copper, and boundary which is high voltage and ground. So high voltage, we will put the value of voltage here. So the gap distance between these two electrode is 4 cm. So also we need to change the boundary value, which is just 110 kilovolt, and we just run the simulation. So we just take the value for voltage. This is the value for voltage, and this is magnitude of field intensity for gap distance 4 cm with 110 kilovolt of voltage. So next we just I will show the value for gap distance 17.5 cm and voltage 362 kV. So the distance is 4 cm, so we're just adding the balance of the centimeter value. So we just we just move this to negative 13.5. So and one way we change the value to 362 kilovolt, and we're just running. So we can get the voltage value here and the magnitude of the intensity. So that's all for me. Thank you. Assalamualaikum.
My name is Omar Sofi Bizamja Arifin, matrix number AE19061. Now we demonstrate the simulation for task 2. So firstly, we do the simulation and we will get this result, which consists of 3 results, which is the first one is flux density. As you can see, this is the value for lower bound and the upper bound, and this is how it will looks like, where the highest density is on the C core, which is near the winding. And for the second one, which is the field intensity, which is, as you can see, the lower bound and the upper bound value. And this is how it will looks like, which is the highest density is at the winding and C core, and also at the gap between C and I core, which is this is due to the fringing effect. While for the current density, the value is only on the upper bound, whereas the lower bound is 0. This is due to the current density only happen on the winding, while for the force exerted on the I core, as you can see, this is the value for force exerted for horizontally and also vertically. Both of it is negative, but for the vertically is smaller in value. So for the simulation, I will pass it to the next member. Thank you.
Before we go for the analysis and discussion, my name is Zidane Binasri with matrix number DE200133. So on the simulation task 2, we have to analyze the exerted force on the CR core magnet. So on the simulation result, we can see on the part which is have the framing effects, leakage flux, and there also mutual flux. In this simulation also, we can detect what region have the highest flux density, or what region has the highest field intensity. So for example, this is on the flux density simulation. So on the core, there has a pink part which is the highest flux density, and also on the field intensity, we can see the field intensity happen outside the core, which is happen on the air gap, and also a little bit on the winding. And also this is the current density, which is on the pink color region, have the highest current density, which is just on this winding, we apply the current on it, which is 50 ampere. So next, we do some improvement on the CI core, which is we analyze when we do increment of number of turns, what happened to magnetic force. So actually, when we increase the number of turns, so the magnetic force also increased, but in linearly, that you can see on the graph. So also we have analyzed what happened when we do increment of the coil current. So we increase 50 ampere each time, so magnetic flux also increase linearly. So as an electrical engineer, we must choose what is suitable coil current and number of turns to make the magnetic force able to lift the load. So, and for the conclusion, there are several analytical results that we achieve on this task 2, which is the first one is we have to understand the concept of electrostatic field in magnetic problems. And also, we have created a model for finite element analysis, which is in the FEMM 4.2 software. And third, also we understand the concept of leakage flux, mutual flux, fraying effects, and the force exerted in electromagnetic system. So that's all for me. Thank you.